Okay, when we are talking about symmetric key cryptography, we agreed that there would be the same key for sender and the receiver. Now, how do they exchange the key between these two? If they physically meet, then they can exchange the key. But if they physically meet, they can also exchange the message. We don't have to only exchange the key. And we also recommend that the key is not used for too long. The key will be changed frequently, if not for every conversation. This could also be for every conversation. So it could be that before I start talking to her or communicating to her by some symmetric key algorithm, maybe a stream cipher, we first agree on a common key. And I use the same key for encryption, she uses the same key for decryption. Maybe next time when we communicate, we don't use that key anymore. We'll also do another little procedure where we can again agree on a common key before we start it. And this is what is called in cryptography handshaking. So before we start communicating, we do handshaking. And this means we agree on a common key. And we normally recommend that the key is not repeated. But not in all practical cases this is possible, where the users are, I would say, ordinary people, could be ordinary policeman or ordinary soldier. They cannot on the fly get into a key agreement protocol and agree on the key. You need some technical expertise to understand what I mean by a key protocol, and if the user is not at that level, then the key may be repeated, okay, till such time. But anyway, we do recommend that we change the key or we agree on the key before every communication. So how do we do it? Again, we have to think of a difficult problem, because here we all depend on a difficult problem. Okay, if we were a part of public key network, PKC network, then we could use RSA. See, if we are trying to talk to each other and we are members of some public key network where RSA is being used, then what I'll do, we agree on the key, that message is my key. The key goes to her and she computes the key by this decryption. So I have my key, she has the same key, and that could be used for our actual symmetric cipher communication. But this may not be true that we are always member of some PKC infrastructure. Okay, but then which is more practical, and this is more used in voice communication. So if I'm trying to call you, try to talk, the voice first gets digitized and there's encrypted by some stream cipher. So we first do a handshaking between two of us before we start actually speaking, and then we have a little protocol by which we'll be communicating, and that's not going to be a public key infrastructure. That may not be. If it is there, then my life is easy, but I would assume that there is not always available public key network. So we'll think of a method of key agreement. So the first key agreement protocol, which is proposed by these two persons, Diffie and Hellman. And Hellman. In fact, this paper is called the birth of modern cryptography. People used to have communication. Enigma machine was used in Second World War. Well, there was used by even Julius Caesar cipher. But there they would be physically exchanging the key. For Enigma machine, they will set a key for each of the machines. Probably it will go for a week or so, and then again they will change it. Caesar cipher, they will pick up a number, and Caesar would probably keep it alive for a month or so. Then again he will change, and so when he will meet the generals, he will just exchange his chosen word. So these are basically on the physical mode. So it was there. So what was not there if I could do it more securely and in some sense provable, the idea of proof, and there was no notion of proof that time. Okay, physical thing. So Diffie-Hellman published this paper, probably a very small paper, a short paper, 1975, and as it is called, 1975 is the birth of modern cryptography. I remember when in 2000 Adi Shamir came for the first InnoCrypt to ISI, he mentioned that this is 25th year of modern cryptography, and he said the birth of InnoCrypt. So he says this is also going to be significant. Okay, and we will celebrate 25th anniversary of InnoCrypt, which is actually this year in Chennai. So what is this Diffie-Hellman protocol? Again, we use mathematics heavily. I talked about cyclic groups. Second, I will have a G cyclic group of large order. This group has to have many elements. Order with a generator G, and this is public. Everybody who would like to exchange key between between two of you, they would know. The whole university know that this is the group I am using and this is my generator. There is no secrecy about it. Because G could be actually my 1, 2 up to some prime number minus 1, P is very large, and operation could be multiplication modulo that n, and then we could find G by using a very simple algorithm. There are plenty of these generators, find one generator, and we publish this one. So G, so this is public. I would say G and the operation and G. This is public. The group, the operation, and the generator that we are choosing, public. Okay, now suppose two persons want to exchange some secret information. Say I want to exchange a key, K. Okay, so first thing, okay, let me just write down. I think you can just write down the slides. So I want to agree on a common key between two of us. So we have to agree on this common key K. So what you do? Well, I would assume all my elements I will be dealing here, they are member of this G. So whatever this key, whatever things I will be doing in between, all these elements that I talk about, they are from this group only. So let me so here is one person A, one person B. They want to agree on a common key. So what we'll do, A will choose A, maybe randomly, a number between 1 and the size of the group. Okay, choose A. She is going to choose B. Again, this is a number between 1 to that order minus 1. Okay. So what you do, in fact, in the real protocol, when you are making a phone call, there would be an option or app in your mobile or your landline. I think when you are working, this is our landline, not really mobile. So there will be option of, do you want to go for encryption? If you say no, the option, if you say no, the dial 1, then you can just go on talking. But if you say 0, that means I want to encryption, then this will ask that you enter a number, say in this range. Even the receiver will first pick the receiver, or she will also be asked to choose this B. And then you don't see anything. What there will be little software embedded in that phone. What they will do, this will compute. G power A. Here it will compute G power B. Now G power A is sent to B. Okay, and G power B is sent to A. Okay, so now G power B is with A. So what he is going to do, and he knows is A, so he will compute G power B power A. And what she will do? She has her own B, she has got G power A, so she is going to compute G power A power B. So what does he have? He has got G power AB, she has got G power AB. So we have the same number in that group. Okay, we have the same number. And now what do public have? Public know G, they know star operation, they know small g, they may hack into the system, they may get G power A, because they have been communicating. So you can hack my communication channel and you can get G power A and G power B. Now from this, is it possible that's my question. Well, if I could solve the discrete log problem, then it's easy. So from G power A, I can compute A as a log. So this is easy if the discrete log problem is easy. And since that is difficult, this is a difficult problem. So even if I give you my group, my operation, my generator, G power A and G power B, from there computing G power AB, which is our agreed key, somebody can compute it, that becomes a difficult task as long as discrete log problem remains difficult. So this boils down to, somewhat equivalent to I write somewhat because I don't show that mathematical reduction. That's why I don't say exact. Then the mathematics becomes more complicated. So assuming an audience were not that expert in theoretical computer science, that's why I say somewhat equivalent to discrete log problem. So this means as long as this problem remains tough, this is very safe. And if this problem is solvable, somebody gets an algorithm to solve discrete log, then this is fall apart. So like RSA will fall apart if we can factor it efficiently. So this Diffie-Hellman key exchange will fall apart if we can efficiently compute discrete log. Okay, and since they are not yet solved reasonably well, we are safe. But again, there is a caveat that if there is a quantum computer, Shor's algorithm will solve this problem also. It will factor, it will also find discrete log problem. So whatever the quantum computer can do, if it comes into existence, now this is no more safe. Okay, so these are not quantum safe. If there is a quantum machine, again we don't know whether there will be any quantum machine at all or not, and when this will be real. As I understand, this is far off from a quantum machine. People put hypes and etc., but it's far from being realized. But anyway, as a humans, we don't give up. We didn't even think that a digital computer will come up 100 years back. So something may come up in another 10, 15, 20 years. But if that comes up, we have Shor's algorithm using a quantum machine, and all these things will be computed very easily. So Diffie-Hellman key exchange will go off. So these are primarily the method of key exchange. If you are, if both the receiver and sender, if they are part of a public infrastructure where RSA has been implemented, then we can use that infrastructure for communicating the key. And if it's not, then we'll be using this Diffie-Hellman algorithm, which is easily implementable, and this is what is actually done. So there are many other now these days, but these two are the early days. 75, this one came before RSA. RSA came in 1977. Okay, and the communications were all basically stream ciphers, or maybe one block cipher. But most of the communication was by stream cipher or by DES, DES, data encryption standard. So DES has been broken by again Ili Biham and his professor Adi Shamir in 1994 or so. So DES, people still use it, but DES is actually not safe, and DES was replaced by in 2000 by AES. And if Shubhamay allows you to go to this IndoCrypt, we'll have one of the lead innovator speaker is Vincent Ryman, who has actually designed AES. So he's the father of AES. I think they invited him once. He came many times. Vincent came in 2002 IndoCrypt as an invited speaker. At that time it was just published, very hot. So Vincent came to Hyderabad. Then in IIT Kharagpur there was a conference in 2008, IndoCrypt. We made him the chair. So he organized the entire conference. And this time in Chennai, he is also coming as a special guest. So he will give a talk. Now what is happening to current days block cipher? Because he told in 2002 in Hyderabad that he doesn't expect it to survive for more than 15 years. But it is surviving. He was thinking human mind, the way it's progressing, maybe 15 years it's safe. But otherwise it's not safe, but it's still safe. So we'll try to learn from him how does he feel about his AES and also about other block ciphers. Where do they stand? So this is again for AES, you need the key exchanges usually by RSA if you are in a network. Otherwise they will be using this Diffie-Hellman. This is how we exchange the key. I still didn't talk about blocks. Blocks will come in my next lectures. I think I'll give another talk on stream cipher. Then I'll go to block cipher, and these are the key exchange protocols. Without.